Hello.
Hello. Hello. All right, that's a little bit better. I will pass off the mic in 1 second. I just wanted to welcome you all on behalf of the Apache Aurora user group. This is the first meeting of this group. It was kind of established in response to an emergent number of companies in the Bay Area that are beginning to use Apache Aurora, which is now a top-level project of the Apache Software Foundation. So my name is Dave Lester. I actually work at Twitter. First, just before we kind of start, I'll hand off the mic, but I'm curious, who here is using Aurora in the room? All right. So my title at Twitter, I'm actually an open source advocate, and I talk a lot to other engineering teams about kind of our software stack at Twitter. But what I would like to encourage you is to all become open source advocates as well, right? Because essentially we have the beginnings, we have a community that's germinating tonight, and this is an opportunity to, I think, kind of grow the impact of this community, also the software, and as you'll hear more about, kind of a burgeoning ecosystem of projects that are built around Aurora. So that's all I really wanted to say. It's really awesome to be here, and I'm really stoked that TellApart is hosting, so thank you very much.
Thanks, Dave. All right, as Dave said, thank you all for being here. We're very excited to be hosting and excited to share our experience as we migrated the TellApart Monolith to something that is more service-oriented and supports many microservices. All right, so this is a little bit about what we're going to talk about today. We're going to talk about the state of the system when we started, so what TellApart's infrastructure looked like. We're going to talk about some big ideas, and in doing that, we want to share what we learned and some of what we built to support our migration. And then we're going to talk about where we ended up. So what the system looks like now, what is coming soon, and then we want to talk about the kind of holes that we faced, some of which are still open, as we went from the kind of perspective of a startup to go execute this transition. All right, so really quickly, talk a little bit about TellApart. So TellApart is a data platform for e-commerce companies to manage customer data and TellApart their highest value customers. What does that mean in practice? A large part of what we do is bidding on ad space in real time on major ad exchanges on behalf of our clients. So there's a lot of kind of low latency requirements, low time budgets for us to process requests that come into our system, and and our developers rely on having really tight feedback loops to tune their bidding and to tune our bidding algorithms and to ingest user data, right? So we want a tight loop, and so that we can quickly act on the new data that we're gathering. All right, so what was it like before? So initially we had a monolithic bidding application. It actually shared space with our ad server and shared a code base. So it took a long time to iterate, and it was very painful as we went to try to spin up new services and applications. It was very painful to do so on the existing infrastructure that we had. And there were lots of inconsistencies in how applications were rolled out. And so you kind of had to be an expert in any particular application in order to be able to debug a problem or kind of traverse the system. And as the company grew and there were more and more engineers, the pool of people who were experts in all of the systems that were deployed into production grew smaller and smaller, and the pressure on those people to debug issues or hold the page or that kind of thing became higher and higher over time. It wasn't really a sustainable situation. So, and I, kind of personally had an experience where I created a small service, and it took way longer than it should have, I would say, to get into production. And so, based on all of that, we kind of saw a need to upgrade the system. So, this is kind of the scale that we're operating at. So we're talking about multiple terabytes a day of compressed data flowing into the system. several 100,000 queries per second inbound traffic, low latency, low time budgets to process our requests, and a team of around, doing all this with a team of around 50 engineers, so supporting them in their efforts. Actually, I'd like to introduce the other speakers at this point. So, my name is Dono, so I probably should let off with that. I work as a software engineer on the monitoring and manageability team, and it's been our responsibility to kind of roll out and transition over to Aurora on top of the Mesos cluster. Cool.
My name is Tony. Oh, that's loud. My name is Tony, and I guess it says on my shirt too. I work on the same team, monitoring and manageability, and I was really interested in this project and jumped on to work on it.
And I'm Dobromir, also infrastructure engineer here. We'd like to take this presentation in perhaps a slightly different direction than most presentations go. So, big ideas. Generally, when people give talks like this, they talk about all the pieces of infrastructure that they created or the open source projects they use, and then they show you lines of what goes where, right? Facts. We like to focus on the ideas. Right? We're going to use the facts to demonstrate the ideas, but our facts are going to be different than your facts. Right? Who here is an infrastructure engineer or works on these kinds of problems? Cool. So when you guys are going to look at these kinds of problems, you're probably going to have very different backgrounds, very different technologies in your stack than we have. Hopefully these ideas, though, will apply to everybody sort of universally. So let's get started. Idea number one. A marginal cost of $0 has unexpected multiplicative effects. Crystal clear, right? So using some ideas here from economics, right? And I want to talk about later how this is going to apply to infrastructure engineers. So who here has heard of price elasticity? Most people. Good, good. Went to college, took the class. So as you decrease the price of something, you would expect that it becomes cheaper, the value increases more or less linearly, right? If you're paying $1 for something and it costs 50 cents, well, no, great, now you have 50 cents more in your pocket, right? General wealth has increased by 50 cents. That's actually not the case. The value generated grows more than linearly because demand increases as costs fall, right? Now that costs 50 cents, that other guy there was willing to pay 60 cents. So now he goes and buys it, and he has 10 cents of value generated. Okay, this is all very theoretical, right? Let's do an example. So, all right, what do you get if you take cheap maps, Google Maps, cheap billing, like every other startup out there nowadays, free location, thank you Russia and the Cold War, and free wireless internet, the phone in your pocket. What do you get if you add these things together? Yes, you get Uber. So this is not additive, right? If you add those things together, you don't see Uber. This is multiplicative, right? You take all of these different things and you go n times m times y times, oh, holy shit, now I get a really big number. I get something that's very, very valuable, right? There's actually a word for this, or a phrase for this. It's called emergent behavior, right? Emergence is a process whereby larger entities, patterns, arise through interactions among smaller and simpler entities, which themselves do not have that pattern. We're going to come back to this theme a little bit. But let's do one more just before we get into how this affects you. Free software, open source, cheap compute, AWS, cheap storage, cheap ad markets. What do you get? TellApart, right? We would literally not exist if that marginal cost hadn't been driven to zero by other parties, right? If the RTB networks hadn't arisen by DoubleClick and Facebook, we wouldn't be able to bid. If AWS hadn't made compute so cheap that a couple of engineers at Google could just say, hey, I have an idea, let's try it out. Oh my God, we got a $20,000 check. Let's find another customer. Oh my God, we have a $100 million revenue run rate, right? That's because all these other things became so cheap that you can start experimenting with things. You can take risks, whereas before those risks would have never been worth taking. Again, I think we're going to come back to. Okay, but let's bring this back to infrastructure, right? We're not building businesses here yet. How does this impact infrastructure? So marginal cost is something that you guys are experiencing all the time on your teams and your companies. You might not be thinking of it that way, right? your high marginal costs are slowing down your iteration cycle, right? So think of every time you want to do a push. Right, I need to run that command, so I have to look it up, and then I have to execute it. It takes 20 minutes to do this. You're paying that marginal cost of doing a push, right? Imagine that you want to, I don't know, build a new package, you want to add a new dashboard, right? All of that is cost associated with it, right? It's not immediate, it's not free. That's slowing down your iteration cycle. If you can drive marginal cost to 0, you're going to get that same productivity multiplied. It's not additive, it's multiplicative. Okay? It's going to become very important in growing organizations. Okay, so let's make this very, very concrete. Question. Everybody get their calculators out. Phones? We'll carry that. Takes an engineer in your 50-person organization 30 minutes to get test code running in prod. They do this 2 to 3 times per day. Your team improves this to 5 minutes. How many engineering hours did you just save? Do we have anybody who like wins these kinds of competition things?
Nikita?
Nikita? Come on, somebody's got to have an answer here. Okay, so you're probably doing the math in your head. You're going 50 times 25 minutes times that's 50 minutes, say on the low side, times 50 people. Okay, that's how many engineering hours I saved, right? No? 100. Okay, is that the right answer? You forgot price elasticity, right? You didn't just save 100 hours. Because by taking it from 30 minutes to 5 minutes, you've increased demand. Right? People aren't pushing 2 to 3 times a day. They're now going 10 to 20 times a day. Because before they had this terrible iteration cycle where they'd be like, oh shit, I need to test this in prod, but that's going to take 30 minutes. I don't know what's really broken, so I'm going to spend 15 minutes adding logging and vars and any other thing that I can do to any part of my code which might go wrong, so that when I push it, I actually get the data I want. Okay, they spend those 15 minutes, they push it, and actually the very first var they added was exactly what they needed. So they just wasted all that time preparing for something because of the long iteration cycle. Now they go, 5 minutes? Oh, that's pretty good. Okay, push it out. Oh, doesn't have what I want. Okay, push it out. Okay, now I figured out the problem, right? So you've increased demand for your product by reducing the marginal cost to 0. So the value increase here is non-linear. Aurora was our 5-minute solution. A big, big part of us getting down to very, very fast iteration. Like we said when we started, before the deploy process, basically you were reinstalling a machine on AWS because we had no freaking clue what you were deploying, right? So we had to install the various Python modules you might want, make sure that everything is up to date, and we had to copy the whole binary over because we didn't know you were just actually changing the configuration file, so we might as well copy the whole binary over. Why not? Could take a long time. Like first server running your new code to be probably 15 to 20 minutes, right? The whole cluster rolling out 30 to 40 minutes. With Aurora, a lot of that got taken away, right? So what are the pieces there? Docker or S3 for storing your packages. You still have to build, you still have to upload, different problem. But hey, you don't have to install anything because now that you're running in Docker, you just have that ready for you, right? All the layers are already there. You don't have to re-download them. You don't have to re-upload them. There's no dependencies on your local server anymore. Rollbacks, super easy. Anything goes wrong, it just rolls back, right? You don't need a human to like look at it too much, perhaps. If you want to restart a random server, that's what, like 2 seconds, right? Anything goes wrong with a particular server, boom, you just restart it. That's fine. No problem there. So let's take this a little bit further, right? So our marginal cost now is 5 minutes. If you go to your boss and say, hey, I can take this down to 10 seconds. It's only going to take like 3 months. You're like, heck no, if I do the math from 5 minutes to 10 seconds, that's 4 minutes and 50 seconds times the number of times that people do this, like, no, it's never going to pay for itself, right? Don't do it. Bad investment. We got bigger problems, right? What happens is you drive your marginal cost to 0. Who knows, right? As you drive your marginal cost to 0, magic happens. Things happen you don't expect. 1 second, 0 seconds. What does your engineering development cycle looks like? When the moment you hit save on your computer, your code is actually running in production. What does it look like then? Right, this is where it's going. If you haven't seen the Google Cloud Debugger yet, I recommend it. This is basically, they're not quite at the 0 seconds yet. I think that's the direction they're going in. But basically, you can debug in the cloud, right? Like you can actually have your application running in prod, you can set a breakpoint, and you can see what's happening. Why the hell would I run the code on my local machine if I can be running in prod? Okay, I'm running in prod. Why the hell would I develop on my local machine if I can just run and develop in prod, right? This means that a couple years from now, we're not going to have IntelliJ, we're not going to have Eclipse, we're not going to have any of the entire freaking ecosystem that was built up around local development. It's just going to be gone, right? Because somebody is driving the marginal cost to zero. This is exactly what happened with Uber. The whole taxi industry is going to be gone, right? The entire transportation industry is going to change because people are driving the marginal cost to zero, right? It's not linear. You get way more bang for the buck than you expect. So, you think your engineering organization looks like this, right? You've got each cranking wheel, it's your engineer, they're doing the cycle. What's an engineering cycle? Well, it's pretty simple, right? You read some code, you write some code, you send a review, you test it hopefully, you submit it, and you push it, right? That's what we do. That's what it looks like. So in this model, let's go ahead and improve one of those pieces by 10%. Great, right? Like this whole cycle is improved 10%. Nice, linear, predictable, right? No. This is what your engineers see, right? They need to get from point A to point B. They have no freaking clue how to get there. There's a shortest path. There's a longer path. There's a path with a freaking line or a cliff, and there's something in the middle. I have no idea what that is. It's probably like a production outage, and then a rollback of your CL, and then probably you have to do a post-mortem. I don't know what that is, but it doesn't look good. Right? That's what your engineers see. So what they're thinking about is, how do I move through this so I can actually freaking get my code out as fast as possible, because I've got this other deadline to go work on. How do I iterate? How do I move quick? Right? So their iteration cycle is, read some code, write some code, read some more code, read some more code, write some code, test it, doesn't work, read some code, write some code. Maybe push it to prod on one machine, doesn't work. Roll it back, read some code, write some code, test it, read some code, right? Send a review, we'll read them like that. Read some, right? This is their development cycle, right? It's not the one wheel. It's lots and lots and lots and lots of tiny wheels, right? Tiny iteration cycles. And they're paying marginal cost on each of those iteration cycles. Every time they do git submit, it's in. I wait 4 seconds, right? My marginal cost is not 0, it's 4 seconds. Okay, it's 4 seconds. Okay. It's not 0. Add all of this up, this is the pain we feel every single day, right? Our marginal cost is not 0. So, why is this really problematic? Well, there's the multiplicative effect, but there's one more very, very important thing I think about marginal cost, driving marginal cost to 0, which is mostly ignored and people don't think about. The really interesting projects, the ones where people don't do because the marginal cost is not 0, are the risky ones. You have a risky project, high risk, high reward. The interesting ones. Oh shit, that's going to take me a week to try that out. Are you going to try it out? No, because you've got the low risk, low reward that your boss asked you to do. So you're going to go do that one instead. Because you know it's going to take only 3 days. If you've done it a million times, it's not particularly interesting, but heck, you have to get it out. So you'll get it out. So when you have high marginal cost, people don't experiment. They don't try the things that are risky. Okay, real life story. Bitter tuning. So background here is a little bit about how does Aurora let you iterate really, really fast. Hopefully not a surprise to you guys using this. But hopefully you guys are actually using it the right way. Code plus configuration. This was our system 6 months ago, right? Yeah. So you actually have a flag file or some sort of configuration file. And when you do a push, it all gets bundled up with your binary and it all gets sent out together. Oh shit, I put the wrong flag in. Okay, I'm going to go change it. I go through the whole process again. I have to re-upload everything, reinstall my servers, right? So the fact that I want to change a single number, for example, takes me 30 minutes. Okay? How many risky projects, risky tuning projects am I going to do? Right? I got more important stuff to worry about than that. Okay, well, what's the nice thing about Aurora? You can break out your configuration from your code. You should break out your configuration from your code, right? Or Aurora files. You can provide what your flags are. You can provide your binary, right? And you can glue that together. So now I can submit a version of my code. I can build a package. I can see my Aurora file, use package version 3. Oh, and by the way, here are a bunch of flags. Okay, version 3 is out. And it's not running exactly how I expected. I can tweak my flags, restart the job, start requiring a push. Minutes, seconds perhaps, right, to iterate. So originally when we did this big migration from Python to Java, started our whole microservices thing about like 9 months ago, we spent 6 months switching from Python to Java for the bidder. Really nice, 10x increase in performance. which was good because we were running, I think, at 1,000 machines or so. So it's starting to be like expensive. Cool. So now they're like 100. That's nice. But we're using 1.5 out of 8 cores. Not very good utilization. Okay. So since I'm actually putting the bidder onto Aurora, I was like, well, maybe I can tune this, right? Now that this whole machine, this whole system's been switched over, tuning is now really simple. All I do is tweak some flags, restart services, right? That didn't work. Okay, increase the number of servers. That's simple. Edit the file, push. Takes me about 30 seconds, right? And within about 4 hours of just playing with number of threads, right? Making sure that we have the right number of paths, etc. I managed to increase the QPS per node 4x. Just increasing utilization. I didn't do any magic. I didn't go edit the code in any way. Right? It was just that experimentation cycle which made it very, very fast. So in the old deploy, this would have taken a week. Clearly, this would have been worth a week of work, right? It's like increasing your utilization 4x, like that's worth a week of engineering work, right? So we would have done that. No, because this was risky. There's no idea if we could actually increase it 4x. If we knew we could, we'd do it. We didn't know we could. We had no idea. Right? I just happened to have a free afternoon going, I wonder if I can make this a little bit better. After about half an hour, I'm like, ooh, that looks better. I'm like up 20%. Well, maybe I can tweak this. I can tweak that. Well, I'm up 50%, 100%, 200%, right? It was very high risk, high reward. And the only reason that we did this, or that I spent any time on this, was because it was zero marginal cost, right? Almost zero. So low that it doesn't matter, right? I could just play with it in a free afternoon and get 4x. So that's sort of what I wanted the big idea here for you guys to be is try to get your marginal cost to zero, okay? It'll really revolutionize the way people work. Aurora is actually an incredibly good tool in many areas for that. Okay, that's idea number one. There is a corollary, which is unfortunately quite long. But let's go through this corollary. So how do you get marginal cost to zero? Right, I guess that's the next question. Right? Like, okay, sure, I buy it and I want marginal cost to zero. How? Where do I do that, right? Okay. Standardized tooling has unexpected multiplicative effects. So really, standardized tooling is how you get your marginal cost to zero. Let's run through this real quick. My 3 axioms of engineering, I made these up yesterday. So most engineering time is spent debugging, probably operations. Maybe not 50%, but like, you know, probably a big slice. Right? Axiom number 1. You don't have to believe these, but if you do, the conclusion comes out. Most debugging time is spent looking for information. Right? You're not sitting there going, I have all the information I need at my fingertips, and I'm just thinking. Right? Like when you're debugging, you're not spending that much time thinking. You're going, why did this person not export this particular variable that I happen to need right now just to solve this problem? Right? What did they? You have to dig the code for half an hour to figure it out. Number 3, most of the time spent looking for information because you're unfamiliar with the system that you're debugging. Okay. We got 3 axioms. Amdahl's law. If these 3 things are true, we should optimize the debugging experience. That's where the bang for the buck is. And if 3 is true, we need to make the unfamiliar systems familiar. So we're not wasting time digging for information. So this is how we accomplish that. Okay? Aurora is the cornerstone of our consistent tools approach. And the key word here is consistent tools. And we'll touch this again a little bit later. But you want people to know where the information is, well, because that's where it is in this other system that I've touched before. So obviously it's going to be the same place here. Why would it be different? It's consistent. Okay? So Aurora gives us a bunch of really great, consistent things we can apply across our entire system, right? So one set of metrics for resource usage, CPU, RAM. We export that all to Librado, so we have like a consistent place where everybody across the organization can always go look at all the data. It doesn't matter what job you're looking for, right? It's just there. Just go look at it. Right? It gives us one UI, so you can go look at logs, right? Or what jobs are currently running, or who's running what jobs. One authorization model, right? So I can tell which user is doing what. One discovery system, and then my favorite. And we're not going to talk too much about the others. I mean, obviously, these are very, very important for our entire. We'll talk about TellApart later. Right? Yeah, we'll talk about that one. I mean, all these pieces are very important for the experience that we've developed for developers. But obviously, this is an Aurora meetup, so we'll focus on that one. And then my favorite one. Everybody here has done import this in Python at some point. Right? Namespaces is my favorite one. Namespaces are one honking great idea. Let's do more of those. right? Aurora gives me namespaces. Thank you, God, right? Like now I have a way to actually talk about the stuff running, right? Cluster, this is just TellApart name system. Stole it from Google in case anybody's been there, right? Bitter was running it, the environment, and what actually is running. This is awesome. I just copy paste this into my metric system. I can see where my metrics are. Or if I want to change from prod to develop, pretty obvious how you do that, right? Don't have to think about it too much. Consistent. So, last story related to this, about the power you get, the multiplicative effects you get when you start tying these things together. Our email team, Sean right over there, they were actually losing 40% of their emails. They didn't even know this, by the way, right? We found out later. It was like some millions of dollars a month. We don't want to talk about how much. They were just going disappearing. Why? They were using some open source library, had a memory leak every so often, right? Get restarted, all the emails in the queue, poof, disappear. There goes your money. All right, well, they're going to move to Aurora because, right, I think it's going to improve their operational reasons, right? Had nothing to do with this problem. But the moment they moved over, they're like, wait, my task service started. Okay, see why? It says my usage is too high. And then I can go look at my graphs, because we have graphs now. I don't have to do anything, I just have graphs. Oh, there's the memory usage, and then it gets reset. So it took them less than 24 hours from when they switched to actually see, wait, there's a problem here. Then, of course, it takes 7 days if we don't have any tooling built yet there to make it easy to figure out. Right? That's the difference in terms of your multiplicator factor, right? We have tools for that, we didn't have tools for that. It took them 7 days to actually fix it. So this wasn't like Aurora or Librado or anything specific, right? I mean, those were great tools. That's what we use to make this super easy, make it free, right? Marginal cost of zero. The idea is you have to get the marginal cost of zero. You have to provide tools for your developers so they don't have to do anything. It's just that the system tells them when things don't happen. So, recap, drive your marginal cost to zero. One of the best ways to do that is use consistent tooling. The problem is now you all have systems that you've been working on for years. How do we get there?
Cool. And I guess I'll tell you how to get there. So we're going to talk about big idea number 2, which is you want to build your system for tourists, not for locals. So what does that really mean? You want to make your system very intuitive and very familiar, so you don't have to be like an engineer that's worked there for years and know every tiny piece of detail about the system to actually do anything, right? And the analogy I really like to think about this problem in terms of is building a city, right? You think of your engineering organization as a city, and you as, I guess, the infrastructure engineers are building out the infrastructure of the city, paving roads, etc. So if we look at, this is a map of London, right? It grew organically out of like little hamlets, towns, little villages, and it grew into this. This is very clear city. So you might be a local city, might be, oh, I've lived here for years, I grew up in this little town. If I drop you into a different part of the city, do you know your way around? Not really, right? Because every piece is different. And I think our engineering organization was starting to become this because we had different components and different infrastructure within different teams and really wanted to unify it and make it one big thing, right? And I think this is a better example of what we actually want to be is New York, right? Think about it. It makes sense. It's a giant grid, right? You know how to, if I tell you, oh, you live in the Upper East Side, go from 82nd to 82nd second to, say, down to Chelsea at 23rd and 12th, you want to say? You know how to get there. It's a giant grid, right? Just go south and west. Not a problem. And that's really what you want to be, is you want to make your system very intuitive. You want to know how to get from point A to point B very easily. Right? And that's kind of the point that we're trying to get across is, I think that engineers and engineering organizations really converge to what I think of as the path of least resistance. Because we figure out how to get things done, right? How to go from point A to point B. And if you make that from point A to point B really convoluted and really hard, they'll figure it out, but it's not the best way to do it, right? you want to lay out the right path to do things, and you also want to make that the easiest path. So I think kind of a personal experience that really drives this point home is we're starting to build this, we're trying to start this transition from monolithic infrastructure into kind of service-oriented, right? So we spun up our Aurora cluster, we built up a lot of the kind of base infrastructure things, and an engineer came to me with this project idea. He's like, oh, I have this great new thing I want to build, and should I put it on your platforms? Yeah, of course, right? We spent time building this, definitely put it out there, right? So I started listing out like, here are all the steps you need to create your service, here are all the steps you need to like generate a config file to like deploy your service on Aurora, here's all the things you need to like make a Docker file and like package it and everything. And then after a while, I thought about it, it's all these steps that we need to take to actually create a new service and deploy it was very long, it's very time consuming. And the path of least resistance at that point was still to basically append this thing onto our existing monolith, right? That's it's not that bad, right? It didn't take that long because we already migrated that onto our infrastructure. So what we really need to do is pave the path of success, right? Pave the right path for people to travel on. Basically have people fall into their success. So what that story really actually became genesis of is something we like to call TellApart server. That name might change now. Anyways, so what TellApart server is, it's a uniform way for us to create new services here at TellApart. And it relies heavily on Microservices. And we saw that as like a great tool for people to use. And along with that, we kind of rolled our own tooling on top of it to make it very applicable to us and make our use case a lot better. For example, building very dependency injection friendly things where you just basically provide some HA handlers, provide some RPC handlers, and it just works. Like just call start, that's it. The reason why we really wanted to do this was basically lower, I guess going back to point one, was also lower the marginal cost it took to create a new service, right? So people don't have to think about creating a new service as a very tedious thing. Because if you think about it, when you want to create a new service, what do you have to do? So you have to figure out how to deploy stuff, you have to figure out how do I write a Docker file, how do I add tooling around it to like debug things if it starts to break, how do I add like alerting and monitoring to a system, how do I like export metrics, everything. It's a lot of work, right? So this really simplifies it. So this is screenshotted our internal wiki. It's a 5-step process to actually create a new HP service on Aurora. It's actually really only 3 steps because the first 2 is just saying, make sure you have your like dev environment set up. If you don't, here's how you do it. So it's just really 3 steps. 1, you first generate this. You generate the service. 2, you go build it. And 3, you go package and deploy it. That's it. And what do you get with that, right? You get a server coming up in less than 3 minutes. So some of you working at Twitter would probably be familiar with this. This is the kind of Twitter server admin UI. So once you start your service, you get this nice little overview of how your system is performing. You see how many requests are coming in, even like what your GC's like, everything. And okay, so and as we're thinking about creating like new services, one of the big things that we really want to think about is one of the big things we now have to think about is RPCs, right? So how does your system talking to downstream services affecting it, right? And tying back to making your system intuitive, if you want to think about RPCs, you just look at RPC set. That's it, right? You go navigate to it, and this is a quick little summary of your system, like all the RPC clients that it has. Gives you a quick like summary of requests and tries and like failures and like latency. This just gets provided to you with your server, and anytime you add a new client, it just shows up, right? And if you're thinking about like making things easy, we kind of as infrastructure people kind of forget that UIs are really intuitive, right? Make a quick little UI. Like I put very little effort to this. You can tell because it's kind of very bare bones. I just literally threw in like I imported Bootstrap and just threw in a table. It looks like this, right? No work really, but it makes conceptualizing what's actually happening in your system makes the summary of it really clear, right? And we get the additional power of interlinking UI. So what does that mean? So let's say if I want to take a look at timeline service, right? It's 99.99 is not great. We want to figure out why. So what do? I just click on timeline service. I get this. I get a list of downstream hosts that this client is talking to, quick summary of everything that's happening. And it just works, right? So now I want to say, look at, say, host 3 is not doing great compared to the other ones. Maybe there's some problem with it. If I click on the link, what happens? It links me back to the admin page of that service. Right? And we want to make this experience where you can kind of debug your system really quickly from beginning to end. You trace your problems from the start of your service to basically the endpoint to figure out where the actual problems lie. Okay, and there's another feature we added, which was /flags, right? So as we talked about with separation of configuration code, this basically shows all the configurations that you actually put into your system. It's actually a real thing. If you notice on the first line, it says allow flag mutation is true, right? So that means that on the fly, you can post to this link, changing some flag live, and without having to restart your service, without having to do anything, the flag update gets propagated through, and now your system is behaving differently. And finally, another thing we added on top of TellApart server is a slightly different health concept. We have now like a health reporter we have a health registry that is taking information from different health reporters, and they're driving what's actually determining the health of the system. So we also have optional modules in there which allows for partial failures. So if part of your system goes down, it's not a big deal. Or it is a big deal, but so another part of this thing you get for free when you create a new service is monitoring, right? You don't have to figure out how to export metrics, how to create monitoring for your system. You just get that for free. So creating a new service, you just go to this nice little dashboard, change the namespace to whatever your service namespace is, and you get everything here. And one of the other important parts about this is you get consistent metrics more than anything else. So you don't have to think about how systems differ from each other. Some engineers might export metrics differently than others. You don't really care. You want the base metrics in your system to be the same, so you can tell when things are wrong right away. And one last thing with metrics is we added kind of Aurora deploy event hooks to the metrics dashboard. So every time you deploy your system, you get like nice events, and then now you can really nicely correlate how each deploy, how each change you're making is affecting your metrics. So we kind of talked about like all these tools that we create to let you create new services really, really easily, right? So now you're just ready to go out and create a new service, or create like services on your new fancy platforms. But the problem is that it's not that simple.
So I think we're going to pause for a second and ask, does anyone have questions about anything that we talked about any of the particular tools or applications? Anything maybe that you haven't seen before? All right, keep going then. Cool, so as Tony said, it's not as straightforward to move to a distributed system as scaling up or out your monolithic system, or even just breaking apart into its components. So, as we went to execute the cutover, we discovered all kinds of ways in which, when the shape of the system changed around the existing applications and code that we had built, new stress points emerged and new breakpoints emerged. Also, there were new requirements that we had to develop new tools to address. So what I'd like to demonstrate here is that the details of the environment dictate a lot of how your application evolves. So these are Darwin's finches on different Galapagos islands, and their local environment dictated very, very different beak shapes. And this is something that we ran into over and over and over again as we went to cut our legacy applications into the Aurora-based infrastructure. So I'm going to tell a story of a specific example. This is kind of what a classic bidder looked like. So there was a bidder application running on an EC2 instance. Sitting alongside it on the same EC2 instance were some helper processes that would aggregate logs and metrics and spin off tasks and that kind of thing. We migrated to something that ended up looking like much more like this, right? So this is, we pulled that VAR's agent out of the individual instance level, so it was no longer a sibling to every single task instance, and kind of created it as, brought it out into its own top-level service. Right now, it's one role in the larger VAR's service. When we did that, right, we now have, you'll notice all of these task instances talking to all of these VAR's agents, right? So we went from a one-to-one relationship on this previous slide. We went from this one-to-one relationship for every agent to this kind of like end-to-end relationship, right? So the structure and shape of the system changed a lot, and that kind of that resulted in a lot of new challenges and choke points emerging in the system. Specifically, VAR's agent aggregates on source, including and as well as some other variables or some other inputs. This is like the data structure, and because the reason that it aggregates on source is so that we can kind of explode out all of our metrics and go look for the source of a problem, right? Like an individual instance or something like that. It's very useful, and it was always kind of supported that you could write as many sources as you wanted to any VAR's agent. We just happened to have one everywhere, right? So we didn't stress the implementation in the way that we are now stressing it in this architecture. So when we went to do that, all of a sudden we discovered, this was the case all along, but we kind of really revealed it, that there's a linear relationship, of course, with the number of clients in terms of the memory used on those VAR's agents. And that ends up being kind of not a great situation when you're trying to run in this distributed system where you want to be transparent to the consumers, right? Like you don't want them to have to think about in any way how many VAR's agents are up and running and what the impact on those VAR's agents is if they, say, double the size of their service, which is something that actually happened. So as we were going and executing this bidder cutover, we were transitioning more and more traffic onto this Aurora cluster, and all of a sudden we hit a point where all of our VAR's agents started going out of memory, and we realized that this relationship was there and that it wouldn't really hold up. So what we ended up doing in that case, we kind of punted on it, to be honest. We mitigated it by enhancing the RPC client, again, the common client that Tony was talking about, to pin to a couple of agents. So the relationship still ends up being linear, but it's a lot flatter than it was. It's a lot harder to hit those limits. I don't think we're anywhere close to them. So separately, second story. We have this awesome service-oriented architecture platform that we're building up and all these awesome common tools. One problem that I'm sure everyone has faced at some point when they've been working in this kind of system is you need to connect outside traffic or traffic that's coming from some system that has no awareness of the dynamic nature of this new system. You need to connect it into these ephemeral ports that your tasks are coming up and listening on. Basically, we built a tool to solve this. I'm going to talk a little bit about it. The unfortunate alternate story name for this is why I had to send 30,000 QPS traffic to dev null, frowny face, because it was, well, that's imprinted on me because it was an extremely painful experience. But I want everyone else to be able to learn from it, so I'll share what happened. All right, so we built this tool called OrProxy. It's it's basically a little load balancer manager. It just watches Zookeeper. This first iteration of actually was extremely simple. It was a script that watched Zookeeper, updated an Nginx configuration, and reloaded Nginx gracefully every time that something happened in Zookeeper. There are a dozen tools that do something similar, Synapse and the like. So it wasn't, I would say, anything special at that point. It was just to kind of solve the bare bones version of this problem. It definitely had some deficiencies, and so I'll go through kind of the initial experience that we had that made us buckle down and make it a lot more robust. So we had the situation where a upstream bidder, or maybe it was a couple of them, went out of memory. Right? So they went down, and the load balancer tier, the routing layer, it ended up doing, I think, what you would expect it to do, or what you would want it to do, and sending all of the traffic that was headed for that instance or those instances onto the remaining pool, right? So Aurora killed the bidder or the bidders, and the rest of the traffic, continued to flow to the ones that were still marked as being healthy by the system. The problem is that the situation that resulted in the initial out of memory got worse when more traffic was going to fewer bidders, right? So we knocked over a few more bidders and made the problem even worse. And people who have worked in distributed systems probably see where this is going. This is a cascading failure and a negative feedback loop. Really, really bad place to be. So that happened, and maybe some instances come back up, and they end up getting knocked over while the other ones are still coming up, and you end up losing a lot of traffic and having your system in a state that it can't recover from. So you might ask, why wouldn't we bring up more instances to handle the traffic? There are a couple of reasons that presents a challenge. One is that they won't all come up at the same time. You kind of need instances that are healthy receiving traffic to handle the load so that none get knocked over as they come up. And the other issue is that, like, as they kind of get restarted, Aurora starts throttling them, and it gets harder and harder to do. So how did we end up fixing it when we ran into it live in the production system? This was handling a portion of our mid traffic at the time because we were mid cutover and just testing this stuff out. The way that we did it was we hit the big red button, turned it off. We got the bidders that are sitting behind the routing layer into a healthy state, and then turned it all back on. And that worked. We got back into a healthy state for the system. It was a really painful, it was a really painful thing to have to do. And you can see on this chart, this is over a couple of hours. That should look very smooth. That should look like a kind of, this is probably on the tail end of the day, so a gradual slope down of inbound queries. And when those gaps are basically lost revenue opportunity for us. So it's an expensive mistake. And actually where we turned it completely off is where you see that big dip. And this is what the Aurora UI looked like, right? Like all of the bidders were getting knocked over, sent out of memory. All right, so what did we learn from that, and how did we improve the system? All right, so we want to make improvements on several layers. And the overarching theme of the improvements is to degrade to stability, right? So like you want the failure case to be kind of graceful. So specifically, on the routing layer in ORProxy, we implemented an overflow sync so that if it has some expectation based on Aurora service discovery of how many instances should be running, and if not enough, this is a configurable thing, some proportion is not running, it will send some proportion of traffic, also configurable, to anywhere else, some other Aurora job if you want it to, like a fallback job or a return an error page or whatever you want, or it will send it to the equivalent, the HTTP equivalent of dev melt, return a file to or something. So then we also implemented configuration setting to allow you to ramp traffic onto new tasks over time. So if there's a slow start kind of problem or a cold start kind of problem, you can control that. For the same reason, we implemented something to do delay sending to new tasks. If there's some cache spin up time or something like that right when the task comes up and is announced in the Aurora service discovery. And then we also we made the ability to push that big red button a lot easier. So it's not like requiring a complete like application change really is what it required at the time and push. It's just kind of a flag. So those are the routing layer improvements that make this less likely. And then on the application layer, we added a concept of traffic shedding. So inbound, if an application is receiving more traffic than it expects, it does the equivalent of sending it to HTTP dev null, which means that, and it logs the fact that it's happening so that we can go correct the error. But the system stays stable. And then the last thing that I'll mention, and Dobomir is going to talk about it a little bit more, and this is something that we're kind of beginning to work on, but there's a lot more to do. This is, that's doing auto-scaling of tasks, right? So when things get overloaded, the ability to scale sideways, right, scale out and handle more traffic would mitigate some versions of this problem. So what does it look like now? So this was a case, this is now a zoomed in chart, right, over, this is, that dip is like a couple of minutes maybe, where the same scenario happened. Actually, it was worse. A third of the bidder fleet ran into OOM within a few minutes of each other and got knocked over and like flapped, basically. And when that happened, Proxy did what it was supposed to do and sent excess traffic to dev null. At the time, I think is how it was configured. And those services came back up. There was a delayed start, traffic ran back onto them, and the whole system became healthy again. That required zero involvement from people, and the system kind of healed itself. So that's much closer to what you like to see. And you can see these are the task instances dropping out as this happened of the bidder, the application layer. Cool. So I'm going to hand this off to Tony, who's going to talk about the last big idea.
Actually, before I start talking, does anyone have any questions? No?
What's the second dip there?
So, as I recall, the first dip is because the first set of tasks failed, and then the other set of tasks still had traffic, right? And the task came back up, but the set of tasks still had the traffic.
Yeah, I think they may have
Yeah.
also hit an out of memory.
Yeah.
Like it was a memory leak kind of situation, and so the whole thing got pushed, and as they approached it, the whole thing got pushed, and as they approached some limit, loosely tied to the amount of time that had passed, more failed, basically.
Any other questions?
Oh, I actually forgot to mention one thing. So we open sourced that tool, basically. So if you have a need for kind of managed HTTP ingress, right, with some Aurora service discovery awareness, you can feel free to use it. It's on the TellApart GitHub account or organization.
Check it out. It's a cool project. So I guess I'm going to be changing the topic a little bit. And we kind of spent the first three big ideas talking about how do you re-engineer your systems, right? The last one we really want to focus on is basically how do you re-engineer your humans, right? Because this is a lesson we learned and kind of didn't do a great job with it, right? Basically what happened was we're working on this system, we're kind of really heads down. We knew all the ins and outs, but then when it came for us to get people to start using it and kept working on it, we didn't do a great job communicating what the processes were, right? And people didn't really know how to do things. And so this is basically what our Aurora cluster looked like the first month. Built this great, big, beautiful thing, had no one in it because no one knew how to use it, right? And no one even knew how to get to it. It's just a big, empty cluster sitting doing nothing. Well, except we're in there somewhere. So the idea is if you build something, they'll come, but not really, right? So you have to actually kind of, have to tell people about what you're building. You have to kind of show them what the tools are, what the new paradigms are, what you're actually doing. And with great people and great engineers, it'll click with them and they'll get that this new way is actually a better way to do things. And well, I guess drawing back to the analogy I used before, having like great big city, right? Or your engineering organization being a city. Imagine if you built the city and you're building now a subway, right? Every engineer that's used to living in the city is now kind of not as familiar with the things you're building. they might be used to kind of taking horses everywhere, right? And now you have a subway, and taking a subway is kind of scary if you don't know what it is or you haven't ever been on it, right? So now, kind of, you have to think of it as every engineer in your system is now a tourist, and you have to kind of play tour guide and show them how to do it, right? How to get on the subway, how to figure out what stops there are, how do you get on, get off, etc. It's kind of very simple thing to think about, but we kind of forget about it, right? So, and it kind of happens. So now Dominger is going to talk about where we are now.
All right, so all the infrastructure engineers are saying, where's my system diagram? And give me lines and pointers. All right, we'll give you one slide with that as well. So this is what our picture ends up looking today, basically. This is our first distributed microservice architecture running in production. Actually, the reason we're all wearing these shirts, these are the project was called Pythia. It took about 9 months, a year or so. And the goal here was to really break up our system from the monolith and microservices. Going to Aurora and a lot of the other stuff we talked about were sort of milestones along the way, right? As we discovered, oh crap, we don't have a way to do this, let's find tools for it. We would find something in the open source world, try it out, and launch a lot of different sub-projects along the route to get us into this architecture. So we changed the engines of our airplane, as the common phrase goes in infrastructure engineering, without too many dips in the graphs. Right? We managed to go from one system to another. Our revenue run rate kept working. Our business didn't fail, and so we all got our sort of mechanic shirts as an award for that. Which is what we're wearing now. So just to go through this real quick, probably no surprises now based on everything you've heard, right? There's Aurora proxy sitting inside the cloud, right? We've got Mesos Aurora are running in AWS. Actually, we'll talk a little about why that's problematic in the next couple of slides. So load balancer comes in, there's your Aurora proxy, HTTP all the way to the bidders. We've got our logs, so that's where you saw the, for example, VARs, or for example, some of the other agents. To Kafka. Kafka we're actually trying to get running in Aurora and Mesos right now. Lots of challenges around that. They're very interesting, but we've been really pushing, trying to the boundaries there and seeing if it's possible. Bidders switch to Finagle and Frift Mux. If you guys haven't tried it out, super high performance. As we mentioned earlier, 20 millisecond average latency. Like our tail latencies have to be around like 99.9%, have to be around the 40 millisecond mark. Finagle Frift Mux is really the only RPC system we found which can do that. And we're slowly actually converting more and more pieces out to use that. So some of these pictures are no longer accurate. For example, we had Voldemort, we were using a serving DB. We had a 2-man Tiger team, actually right here, rewrite the entire database system on top of TellApart server, pulling out the pieces of Voldemort that were good, and putting in Aurora, right? Guess how long it took them? 3 weeks. They built a whole freaking new database in 3 weeks, which is better performance than Voldemort had, easier to manage because it's now running on Aurora. We can swap it nightly, just bring up a whole new set of machines, take down, or a new set of jobs, take down all the jobs, everything's transparent. So that's the kind of power that this kind of infrastructure gives you. You can iterate super fast. When they came and said they could do it in 3 weeks, we were like, you guys are crazy, this isn't possible. But they did it. Right? And that's because a lot of the tooling there just makes it so you can iterate quickly, right? And that's really what you want to give your engineers so that they can do crazy shit that you think they'd never be able to do before. So we have right now identity and timeline services. These are sort of our microservices we built below. At this point, it's really nice to have these really thin layers, which a couple of engineers can iterate on, right? They can push whenever they want. They're not tied to the bidder push cycle. At this point, the bidder, which remember we broke out originally in order to have different smaller pieces. At this point, we look at the bidder and we go, damn, that thing's a monolith. We just wrote that thing. Right? In the last 6 months, we just wrote it. And at this point, we're looking at going, maybe we can break this up into smaller pieces, right? So that each of these teams has less marginal cost in iterating, right? They don't have to wait for the daily push. They can push 3 times a day if they want. It's fine, right? Because they don't affect all these other engineers. They can move as quickly as they want. So we expect this picture to become much more complex over the next 6 months. Of course, with other partners that we're going to be working with soon, this picture is probably going to become unmanageable on one slide very quickly. So wanted to finish real quick with holes in the Mesos and Aurora universe, specifically for startups, but might also apply beyond startups. So next one might be a little bit controversial. I think I've had discussions with some of you, and people aren't always on the same page here, but I do want to bring it up because it's something that I find personally very painful and I think has been problematic for us. So this is the model, right? Mesos, lots of frameworks. There's your Aurora framework. Hey, you can try running Hadoop directly on it. Spark has its own framework, right? This is great. Right? Everybody can write their own framework and get this stuff running on Mesos. Now this is a bug, right? Why is this a bug? Well, let's go back to sort of all the big ideas we were using earlier. Right? We want to have low marginal cost. Well, crap, now if I'm running 6 frameworks, if I want to do something, I can't just do it once and boom, it's free for everybody. I have to do it 6 times. And if somebody else installs a new framework, which I don't even know about because they can, now it doesn't work for them anymore, so the marginal cost only increased. Ooh. 2, you don't have consistent tooling anymore, right? Every application runs differently. If I go to the Spark UI and I want to look at logs, can I? I don't think I can. Right? I think the logs aren't there. I actually have to SSH to the machine to look at the logs. Why? It's like such a dumb, easy thing to build, right? Aurora has it. Why can't they have it? Well, it's different. Okay, they don't have it. Fine. So now suddenly every tool works differently. This doesn't work for tourists anymore, right? If I'm an application engineer working on Aurora because I work on the bidder, and somebody said, hey, can you go work on this MapReduce problem? I go, yeah, sure. Oh wait, everything's different here. Like, where's my subway map? Please. They don't know how to get around anymore, right? Everything is different. It doesn't have to be, right? So I really, really think that this is problematic. This is not what we want in the long run. So I'd really like people to think about how can we end up with a system where you have consistent UIs, consistent tools across all of these different applications, and really only the minimal amount that they need to customize, maybe the scheduling. If something as small as possible, you give control to them so they can use it, but overall it looks just the freaking same. Right? And perhaps I'm a little spoiled. That's what we have, of course, on board with Google. They know it's possible. So it'd be really nice to figure out how to do it. And the next one. So, dollars. We run in the cloud. The cloud charges us per hour. Mesos and Aurora don't deal very well with that, right? You build up your cluster, you've got your 100 machines or whatever, and then you schedule on them. What happens at night? Well, we've got a bunch of jobs running at 100 tasks. They don't need 100 tasks, they could run 30 tasks, right? I looked at this today real quick. I think we're running about 40% overhead. It just doesn't need to be there because of travel. What can we do about it? Nothing. Right now, it requires you, a human, to go in and lower the size of this cluster, which we sometimes do when our clusters get too hot and we have to bring up tasks because things have moved around. Right? Or we have to build cron jobs or whatever. This is dumb. Right? Again, marginal cost to 0. This should be free. Any developer working on top of this system should be able to simply have, same as they have an update config, right? Or a health config. They should be able to have a autoscale config, which says, hey, here's my load Z, just like my health Z. Right? If it gets to 1.9, spin up another task, right? And your scheduler should just be looking at that and automatically be adding and removing tasks as necessary. Right? This should be completely free, 0 marginal cost. So it's something that we're looking into, that we might actually do, because at this point it's costing us 40% waste. What about the actual machines, right? So this is great. I'm bringing tasks up and down, let's say. Well, I still have machines lying around, so I'm still paying for them, so it doesn't really help me that much. So why doesn't Mesos have a concept of, what does it mean to bring up a machine? Well, in the fixed cluster, it doesn't happen very often, right? But in the cloud, this is a really interesting problem, because you've got high RAM machines, you've got high CPU machines, you've got high disk machines. Oh wait, suddenly we have this awesome optimization problem. Engineers love optimization problems, right? You can look at all the resources you've got. You can look at all the resources you can buy. You can say, oh, I got too many high RAM machines. Let's start turning those off while I turn up more high CPU machines, totally automatically, 0 marginal cost. Developers should not think about this crap. Right? Why are developers thinking about which kind of machine type I should be running on? They should just say, I need 100 gigs of RAM and whatever, right? And it should schedule it. You should find the right machine, turn it on, and it's not on for you completely automatically, right? Becomes an interesting cost problem. Amazon gives you spot instances, reserved instances, by the hour instances, right? You can think about your job and say, how much am I willing to spend on this job? Priorities for that, or some other, hey, I'm willing to pay up to $3 an hour for this job, right? Okay, let's spin up instances because suddenly the cost is falling, make your job be faster. This is actually something that we're building sort of a one-off for our MapReduce, right? Our MapReduce team has spent a lot of time thinking and building this, and we can't use it anywhere else, right? It only works there. Well, right? It doesn't work everywhere, right? It should just be part of the cluster management solution and completely free of us. So, yeah, this is mostly startup. Right, mostly if you're on AWS. But I would actually argue that Twitter, or any other company that has fixed data center sizes, is going to need this as well. Why? Well, for the last, I don't know how many N years, Google's been fighting a utilization problem, right? Where, we've got somebody who actually works on that here. So utilization of Google is really, really low. Okay, how do they fix that? They take a stick, freaking increase your utilization, or I'm going to take machines away. Engineers don't like that very much, right? Or they use the carrot, like, what more machines? Can you please increase your utilization? Right? Not very effective. We never have a utilization problem because we just auto-scale, right? We say our utilization is going to be 80%. If it drops below 80%, get rid of time machines. If it goes above 80%, add machines automatically. You don't have to worry about it, right? So if this was built directly into that infrastructure, and if companies started billing, Twitter started billing by the hour, then suddenly you have all these incentives to do the right thing, increase utilization, right? Just auto-scale. Zero marginal cost. I don't have to do anything as a developer. It's like a 3-line config, right? And I have to export a load Z. Okay. No work. Suddenly my utilization's good. Suddenly we have all this spare capacity. Hey, we can now run our map reducers at night for free because these resources are suddenly becoming available with no additional human work, right? Emergent behavior. All right, that's it. That's tying all the themes together, hopefully, that we had. This was probably a bit longer than we had originally expected. Hopefully, it was interesting. Hopefully, you got something out of it. Would love to take questions if there are any. Is this all clear as mud?
No softball question?
Softball questions? Any of this convincing in any way, especially the big ideas. We're like going out on a limb here, trying out to see if anybody's interested in this stuff.
So, since we ended up with the, how do you call it, controversial and dollars, and probably you know that Uber is also controversial, and what we described in the last part, which is perfect elastic supply of machines, and basically you are pushing your problem, your cost problem to your provider, and you expect your provider to be able to give you infinite amount of resources when you need them, and then take them back as soon as you don't need them anymore. And actually this is why utilization is hard at Google, because Google owns resources, and this is why it was hard for Amazon, and this is also probably why Twitter didn't implement that, because they have fixed resources, right? So they didn't need it. They don't run on somebody else's hardware. And question would be, what if everybody does this, right? I'm not sure how much it can scale. I mean, if all the taxis and all the public transport goes away and everybody is on Uber, Uber already started checking up prices when there is high demand. And people started to scream already, right? Won't that happen again?
I think there are a bunch of different questions there. I think for the last question, Tony has his favorite answer.
You slipped.
Yeah, we debate that all the time. I think for the pricing, sure, there's always going to be competition. There's going to be a couple major players, right? I can imagine that at some point, 5, 10, 15 years, I don't know what will happen. A lot of stuff will become commoditized, right? I imagine at some point, a company like Twitter or Apple, wherever, will be able to sell their spare capacity because it'll be so damn easy to do that why not do it, right? Of course, we're very, very far from that. You can imagine what happened at some point, right? Same thing happened with electricity, right? At some point, it's like, well, yeah, it's just there's a grid and they throw it on there, and I don't care where it goes, it just works, right? We're very, very far from that, and imagine what happens probably within our lifetime at some point. For the question, what was the other question? It was about, the fixed resources. So I think you're right that it doesn't make sense for companies to do this when you've already paid for your fixed resources and there's nobody else to take it on, right? What is the solution to that? The solution is to oversubscribe, right? As long as there's always more demand and capacity, then the motivation is there, right? How do you get always more demand and capacity? Drive your marginal cost to zero, right? Just make it cheaper and cheaper and cheaper, and then the demand keeps increasing because people are like, well, if it's cost me 0.01 cents, hell, I'll throw some crazy job on there, which will do, I don't know, Bitcoin mining or something. Because at some point you go, yeah, it's cheap enough, I'm going to do it, right? So right now, a lot of the costs that we would probably export from Google because it's just too high. But as more and more resources come online, as long as this infrastructure sort of standardizes, like today as a developer, I can't, what's the word? I can't arbitrage between like Google and Amazon, right? If Google drops their price 20% tomorrow, we're screwed. Like, oh, tough luck, we can't do anything about that. It's not, the marginal cost of switching is way too high. Right, we even talked about it somewhere, we're like, is one of our goals with the Aurora transition to be able to switch providers? We're like, no, too thorny an issue. Like, let's not even touch that. If it happens, great, but let's not even touch that. But someday, that will happen. Right? Someday, it's going to be a utility. And you always say, I don't care if it's running on Twitter, Amazon, Google, whatever, right? Doesn't matter. At that point, oversubscribing will be particularly easy. These are all complete opinions of mine with no foundation in reality whatsoever.
You will care about data online. It's the problem when you own
It's a problem today.
no,
It's a problem today, yes. Will it be a problem in 20 years?
from the East Coast to the West Coast and have 20 milliseconds ping between those two in your data and your CPU. It's a problem.
I agree, it's a problem today. I refuse to believe that it will be a problem forever. Because every problem that people say is a problem forever has somehow not been a problem forever. Other questions?
Slides going to be available somewhere?
Yeah, we're going to publish the slides so anybody can look at them. And we'll also publish the video if it worked. Hopefully it worked. If it didn't, we'll force all these guys to do this one more time tomorrow, right? We'll do it better tomorrow, yeah. Come back tomorrow, it'll be even better.
Now that we have practice.
Cool. Thank you very, very much for coming and for listening. And we're going to be hanging out here and actually quite hit bars. I think if anybody wants to join us. So happy to hear questions one-on-one as well.
Thanks.